Rate laws. One can gain information about the rate of a reaction by seeing how the rate changes when you change the concentration. In the reaction, ammonium plus nitrite yielding nitrogen gas and liquid water. We did 6 experiments. So let's compare the first 2. Okay, draw a line like that. What's the difference there? Well, we doubled the amount of ammonium, the concentration of ammonium for the second experiment. We went from 0.01 molarity to 0.02. Then we looked at our initial reaction rate. Remember, we do the initial because that gives us the most information. And we find that for the first experiment, it was 5.4 times 10 to the minus 7. For the second, it was double that. So when the concentration of the ammonium doubled, the initial rate also doubled. Let's go to experiments 5 and 6. So let's draw a line here. And notice here we're keeping the concentration of the ammonium constant. And that's a pretty standard experiment, right? You keep one thing constant, vary the other one. And what did we do here? We doubled the concentration of nitrite. Went from 0.0404 to 0.0808. And once again, what do we notice about the initial reaction rate? Well, we see that doubled also. In chemistry, when we observe something, we see if we can fit it to a law or make a new law about it and then test it with other reactions. So in this case, what are we proposing, or what did we see? The rate of reaction is proportional to the concentration of each of the reactants. So this little alpha sign here, that means proportional. And this is the concentration of ammonium. This is the concentration of nitrite. Let's combine them into one. So the rate will now be proportional to the 2 concentrations multiplied by each other. And then a handy trick to get rid of the proportionality sign, we come up with the constant. So now we have equal some kind of constant times the concentration of the 2 reactants. This equation right here is called the rate law, and K is the rate constant. The value of K is a very specific number, very specific constant for a reaction at a given temperature. A rate law shows the relationship between the reaction rate and the concentration of reactants. The exponents, which you haven't seen yet, they'll tell you the order of the reaction with respect to each reactant. So let's say we had reactant A and reactant B. Experimentally, we'll determine these exponents. So if you have 2 here, that would mean that's second order. Okay, and that 2 just applies to the B. For this reaction, where we determine this via experiment, we determine the exponents, which in this case are just going to be 1. So because the exponent for each reactant is 1, the reaction is first order with respect to the ammonium and first order with respect to nitrite. The overall reaction order can be found by adding the exponents on the reactants in the rate law. You can see here we put the 1s there. You really don't have to. If there's no 1 there, you assume it. So you add 1 plus 1, yay, 2. This reaction is second order overall. That means that if the concentration of either reactant is doubled, the reaction rate will double. If the concentration of both reactants is doubled, the rate of reaction will quadruple. It'll go up by a factor of 4. Let's look at another reaction. We have nitrogen dioxide going to dinitrogen pentoxide, right here. And we're going to tell you that this is the rate equation. Some constant times the concentration of nitrogen dioxide with a 2 in the exponent. This means that if the concentration of the nitrogen dioxide is doubled, the rate of the reaction will quadruple. It will multiply by 4. This, let's see, the second order here thing has absolutely nothing to do with that 2. This was determined experimentally. One more example. We have azane here going to nitrogen and hydrogen, and it was found experimentally that the reaction is second order in azane and second order overall. So here's our rate equation. That means, and you can see the second here, the 2. That means if the concentration of azane is doubled, the rate of the reaction will quadruple. The decomposition of dinitrogen pentoxide. And actually, now that I look at this, the previous slides I was calling the O4 pentoxide. That should have been tetroxide. Sorry about that. All right, but in either case, we have this going to nitrogen dioxide plus oxygen, and we're going to tell you that the above reaction is first order with respect to the dinitrogen pentoxide. And here's the statement that I've been making. The coefficients do not relate to the order of the reaction of that particular reactant. The order is determined experimentally only, right? Because if you saw this too, you'd immediately jump to second order. Nope, has nothing to do with that. So this is first order with respect to dinitrogen pentoxide. Here we have nitrogen monoxide combining with hydrogen to form nitrogen and water. The reaction determined experimentally is first order with respect to hydrogen and second order with respect to the nitrogen monoxide. Even though 2 molecules or moles of each nitrogen monoxide and hydrogen are reacting in the above reaction, the reaction is not fourth order overall. Recall, the coefficients are not related directly to the order of a reactant or reaction. The order of a reactant or reaction is determined only experimentally. So if someone would give you this equation and say, go ahead, what order is this? You'd say, sorry, can't do it. I need an experiment to tell me. So you cannot predict the order without observing, in some way, the actual physical manifestation of the interactions of the particles in the reaction. The reaction is first order with respect to hydrogen and second order with respect to nitrogen monoxide. So when we're giving those facts, we can certainly write the rate equation. This means that if you double the concentration of nitrogen monoxide, the rate of the reaction will quadruple. If the concentration of hydrogen is doubled, the rate of the reaction will double because it's only first order. If the concentrations of both reactants are doubled, the rate will increase 4 times 2, which is 8. The rate constant, little k, will change only when the temperature changes. So let's look at this graph here. You have temperature going in this direction, and here's the rate constant going in that direction. Right in the beginning, it doesn't change much. Then all of a sudden, when you get to a certain temperature, right around 200, it starts going up like that. Generally, as temperature increases, so does the reaction rate. That's because K is temperature dependent.